We drew the design, tested it, and verified it. But we still have an incomplete ghost on our hands. Not a single transistor knows the code we wrote in Verilog or VHDL yet. Not a single piece of silicon carries this logic yet. Verilog, VHDL. These are intentions, a designer's logic, committed to text. But silicon does not understand intention. Silicon understands only physics. Voltage, current, and gate transitions. You have not yet converted your RTL code into physical reality and brought it to that form. This is where the synthesis process enters the picture. This is Axiom Tech, and I am Epoch. In this video, we will see how your RTL code is transformed into a physical gate network. The synthesizer is a compiler, but not an ordinary compiler. A C compiler converts source code into machine code. The synthesizer converts RTL code into a logic gate network. The output like a circuit recipe made of physical transistors. Think of it this way. An architect draws how the building will look, but that drawing does not start construction. A structural engineer takes that drawing and converts every material, every connection, every measurement into a concrete construction plan. Your RTL code is that architectural drawing. The synthesizer is the structural engineer, and the output is the construction plan. We press run synthesis in Vivado, and the synthesizer begins its work. Synthesis consists of 3 separate stages. Each one takes the output of the previous and transforms it. First stage, the elaboration. At this stage, the synthesizer reads the RTL code, recognizes the modules, understands the hierarchy, and checks the syntax. No gates are created at this stage yet. Only the structure of the design is understood. You can think of it like building a table of contents for a book. The content is not yet written, only the structure is extracted. Second stage, the optimization. At this stage, the synthesizer simplifies your logic expressions and removes unnecessary gates. It seeks ways to produce the same result with fewer transistors. A and A or B is simply equal to A. Of course, the synthesizer knowing this and deletes the unnecessary gate. This stage is technology independent. There is nothing FPGA specific yet. You can see only pure mathematics. Third stage, technology mapping. This is where abstraction ends. The optimized logic is mapped to real primitives in the target FPGA's library. For the Xilinx UltraScale Plus, these are LUT 6s, FDRE flip-flops, and carry 4 chains. Every abstract and gate now becomes a real LUT configuration. The design is now written for this specific silicon. To understand the output of synthesis, you need to understand the LUT, lookup table, the most fundamental computational unit, the search engine of an FPGA. Inside it lives a 64-bit memory, and for every input combination, a pre-computed output value is stored inside the LUT. A 6-input LUT can handle 2 to the power of 6, that is 64 different input combinations. For each combination, the output value is programmed, and, or XOR not, any logic function can be expressed with this 64-bit table. The LUT is a universal logic machine. Imagine a cipher decoding table. The plaintext corresponding to every encrypted code is written in advance. The agent sees the cipher, checks the table, and takes the answer. No computation, just lookup. That is exactly what the LUT is. It searches instead of computing, and that is why it is extraordinarily fast. This always block from the Ghost's AXI-Stream parser, mapped by the synthesizer to 3 LUT 6s and 2 FDRE flip-flops, 12 lines of Verilog, 5 physical primitives. This transformation happens across the entire design, for every module, for every line. Synthesis is complete. We no longer have Verilog. We have a gate-level netlist, a file in which every gate is defined, every connection is listed, and the entire hierarchy is flattened. This file is the DNA of our design. Look at this network. The Ghost's AXI-Stream parser, BRAM controller, DSP RISC engine, fixed message generator. All of them are now here as gates and wires. Abstraction has vanished entirely, and only physics remains. Think of an electrical grid map of a city. Every building is a consumer. Every transformer is a gate. Every cable is a connection. The map shows you the entire city in a single document. In this document, you can see every connection, every load, and every flow path. The netlist is exactly that. The Ghost's electrical map. The place and route stage will take this map and position every gate at its exact physical location on the silicon. The synthesis report opens. We look at how much silicon is needed to run the Ghost's entire architecture. 4,847 LUTs, 3,201 flip-flops, 12 BRAM blocks, 8 DSP slices. In total, less than 2% of the Xilinx UltraScale Plus resources. 2%. The Ghost uses 2% of this chip's capacity. This is not efficiency. This is surgical precision. Nothing unnecessary exists. Every gate serves a purpose. Every flip-flop holds a state. No silicon is wasted. We look at the timing report. Critical path delay is 3.84 nanoseconds. Our target clock period is 4 nanoseconds, 250 megahertz. Slack is positive 0.16 nanoseconds. At synthesis level, timing constraints are met. Synthesis is complete. The Ghost is no longer an idea. It is a circuit recipe, but still not silicon. In the next encounter, place and route, every gate will be seated at its exact position on the silicon. Every wire will be routed through physical metal layers. The Ghost begins to crystallize. This is Axiom Tech, and I am Epoch. I will see you in reality.